is this?
It's 13. Lucky number 13. Good. Okay, so we will continue limits, and since
Damn, if only it was Friday.
if only oh, Friday the 13th, right?
Yes.
So if we remember, just to contextualize what it is that we're doing, we notice that in calculus we're going to consider a broader range of functions than the ones that we might be used to. So to emphasize this, I've included a quote also from Spivak's textbook, which maybe this has become obvious to you now, but Spivak likes to emphasize one thing should be abundantly clear from these examples. A function is any rule that assigns numbers to certain other numbers, not just a rule which can be expressed by an algebraic formula, or even one with a uniform condition which applies to every number, nor is it necessarily a rule which you or anybody else can actually apply in practice. So I think, Logan, you commented on that taxicab number, I don't know, TC of n or whatever it was written, and objected that this is somehow not a legitimate function. But any rule which takes in numbers and assigns other numbers has the designation of function. And as we'll see, the stars over Babylon we'll look at, which seems really quite complicated, and this more general class of functions that we're going to study in calculus, it would be nice to have some way of discussing whether those functions have sort of nice properties that are similar to the functions we're used to. So functions we're used to are like lines and parabolas and curves. So I'll just draw a kind of familiar looking function like this. This function, which kind of has this nice smoothness property, right? That it doesn't jump around quite a lot. If you move a small distance in x, you only move a small distance in y. There's no giant jumps. So this function roughly has the property that as you get close to some value x for its input, you get closer and closer to some particular value f of x for the output. So it kind of has this sort of locality property. If I'm close to an input, I'm close to the corresponding output. Other functions need not have that property. So for instance, we could consider a function like a step function. So this is actually quite important in physics. This is sometimes called the Heaviside step function, theta of x. So,
Christian, pause for a moment. I think Logan exploded.
oh no.
That happened. Can you hear me?
Whoa, you sound scratchy. What happened?
I had my hand over the mic there. I stopped sharing my screen and then everything broke.
Oh, okay. You still sound like, I don't know,
You
low.
sound really tinny.
Not like tinnier than before.
It sounds like you've taken your microphone and stuck it into a tin can. Or made a microphone out of a tin can.
Actually, it's getting a little better. Is there
Why
something
not
else?
both?
Okay, now that sounded reasonable. What was the last thing you heard?
I'm gonna say we are still back on the quote.
Oh my gosh, that far back. Okay. Wow, alright, so the motivation, well, let me just start over then.
Okay, it was when you wrote down Stars of Babylon.
Okay, good. So we saw the quote, which is emphasizing that there's lots of things that are considered functions, not just the nice lines and formulas we've written down. Then I showed Stars over Babylon, which we'll ask about shortly, as an example of a kind of strange-looking function. This doesn't look smooth at all. It looks very jumpy. It assigns these kind of disconnected points to various places. That popped up, and I didn't want it to. So the first kind of, since calculus is really a systematic study of functions, or analysis really is, which calculus is a subset, it's nice to have certain rigorous properties that we can ask, do the functions that we're talking about have that property? So we can kind of classify them, constrain them, and describe them. And then after discussing Stars over Babylon, I came back here and said, the functions that you're used to dealing with probably in an algebra class, like the f of x I've drawn on the left, this is kind of like some smooth, I don't know, cubic or something, and f has the property that if you only go a little distance to the left or right along x, along its input, you'll also only change the output of f of x by a rather small amount. It doesn't jump around very much. So for instance, if you get closer and closer, if you plug in points that are very close to a particular value x in the input, those outputs are going to get closer and closer to the corresponding value f of x in the output. So this function has nice, well-defined limits, right? If you get a limit as the input gets closer and closer to some x, the output will get closer and closer to f of x. It behaves in this kind of well-behaved, smooth way. One function that does not have that property is sometimes written theta of x, the Heaviside step function. So this is a step function. It's very important in physics. The step function is 0 for all negative values of x. It's 0, and then it jumps up to 1. Jumps up to 1, and then it just stays 1 for all positive values of x. You could write this in a piecewise way if you want. It's 0 if x is less than 0. It's 1 if x is greater than or equal to 0. So this is the Heaviside step function. Here's x, here's theta of x. Now, this function is very different from the ones you've probably dealt with before, because if we look at its behavior near x equals 0, it does not have that nice smooth property that the closer and closer you get to 0, the closer and closer the function output gets to some one single fixed value. Because as you see, if I get closer and closer to 0 from the left, the output stays close to 0. But if I get closer and closer to 0 from the right, the output stays at 1. So it's not true that it approaches some constant fixed value. This function has what we call a discontinuity. The limit does not exist at the point x equals 0. So in some sense, the entire purpose of this chapter is to turn this intuition, which we get by staring at a graph and asking, does this look jumpy? We have to turn that into rigorous mathematics so we can write definitions and tell whether a function has a limit which exists at a point or not. So, good questions or thoughts on this?
No?
Nope.
No. Okay. All right. So, last time we developed this definition, and I will state the definition for you now. And again, this is probably, not probably, why am I hedging? This is without a doubt the most important definition in all of calculus and probably in all of analysis. I'll hedge the latter. So this is the definition of a limit existing, and it's the delta epsilon definition. So we say that the limit as x approaches some value a, so I'll underline limit because that's the word that we're defining, the limit of a function f of x, as x approaches a, so x is getting closer and closer to some input point, approaches a, equals L. So capital L will be the value of the limit. So we say that the limit of f of x as x approaches a equals L, and I'll write that again in symbolic notation. So these are the words. We say that f of x as x approaches a goes to L, and write symbolically, you'll see this written lim under it x goes to a, which in LaTeX is underset of f of x equals L if, and this is the thing which you simply must have tattooed on your arm or something. I mean, this has to be constant time. I will make daily challenges that ask you to just write this from memory, because you don't have to memorize the words with no meaning. You can reproduce them. I can just think about what do I think a limit should be and reproduce this definition by working it out in my head. What is the limit supposed to do? Well, we know that the value of the function should get closer and closer to the expected limit value, which is L, as x gets closer and closer to a. So what does that mean? That means if, I changed the color, for every epsilon greater than 0, which we think of as sort of the tolerance in the output value away from L, there exists a delta greater than 0. Delta greater than 0, such that, and this is the key part, if 0 is less than the absolute value of x minus a is less than delta, so this means x is within a distance delta of the target input value a, but this 0 on the left is important because that means we're not considering the point where x equals a, so x is within delta of a but not equal to a. If that's true, then absolute value of f of x minus capital L is less than epsilon. Okay, one more time. We say that the limit of f of x as x approaches a equals L. In particular, it exists and equals L. And we write that as the limit as x approaches a of f of x equals L. If, for every epsilon greater than 0, every output tolerance, there exists an input tolerance, so that if I am within the input tolerance of a, then f of x will be within the output tolerance of L. All it is. Getting us close to an output by making us close to, but not equal to, an input. Okay, there should be questions on this, I hope, since this is the magnum opus of mathematical analysis.
It seems weird to have this absolute value and the such that if 0 is less than the absolute value of x minus a is less than delta. That looks weird in my opinion.
This
Yeah, that's what I
inequality.
was going to say too.
If you prefer, you could write this inequality as saying, the reason we write it as this inequality is because it's shorter than doing it the alternative. So what's the alternative? The alternative is, or you could write, let's see, so a minus delta is less than x is less than a plus delta, but we need an and x is not equal to a. Right, so that's kind of a pain to write both of those, because we need x to be within a distance delta of a, which I've encoded in this first one. If it's within a distance delta of a, it had better be between a minus delta and a plus delta. So that's the first part. But you also have to insist x is not equal to a, which gets you this left side. So if you prefer, you can write out the definition that way. Does that look more intuitive to you this way?
Slightly less, but it helps me understand the former.
Oh, you think this one's
more
less?
intuitive, but it seems less useful now that I see what's going on.
Okay, good. Yeah. I think we wrote it out this way a couple times last time when we were doing the same problem 3 times with the lines. Remember that? I kept writing it this way. And, yeah. This is more concise, though. Same thing here. This one, maybe it's even better, because we don't have to worry about the 0 piece. We would just say L minus epsilon is less than f of x. It's less than L plus epsilon. So there you don't need the and, whatever. Okay, let me just draw it to make sure we're all visualizing the same thing. So we can draw it for a line again, since the linear case is kind of the easiest one to write proofs for, but we will of course write proofs for many functions that their limits exist. So here's just a line which I've drawn close to slope 1, and maybe there's some limit value L, and we want to guarantee that the output of this function is between some L plus epsilon and L minus epsilon, which I've drawn kind of bigger than epsilon on one side than the other, but be generous with my artwork. To do that, to guarantee that the output lies between these bars, L plus epsilon and L minus epsilon, all we have to do is guarantee that the x value lies within a certain range, a plus delta and a minus delta. And my pen's lagging. There we go. A minus delta. So for a line, we started to prove last time, for a line, the limit will exist at every point, because at every point, to get it within some epsilon bars of the output, you can find the appropriate delta bars of the input, and to find the relationship between delta and epsilon, you just need to find the slope of the line. So this is just a picture. We're not proving anything. I'm just illustrating the definition. Is this okay?
Yes.
Good. Okay, now I will ask you some exercises. So this is exercise 2.1.1 in the AOPS book, so 2.1.1. And this asks, so give an example of a function. So you're asked to cook up a function. Give an example of a function f for which the number 0 belongs to the domain of f. So that means f is defined at 0. We're allowed to plug in 0. But where the limit as x approaches 0 of f of x is undefined. So give me a function where the limit at 0 is undefined. Any function you like.
This is just a total guess, but could it be f of x equals 1 over x?
F of x equals 1 over x. So is it true that 0 is in the domain of that function?
No.
No. Okay, so that fails our first test. It passes the second test. So if you were just asking a place where the limit as x goes to 0 of f is undefined, that would be fine. But we also want 0 to be in the domain. So I'll have to try.
Oh, so we could just make another piecewise function where if x is less than 0, then y equals 1. Trying to think of how to word this right.
So x less than 0, you output 1. Okay, then what?
And if x is greater than 0, then output 2. Different one, but yes, this
X is greater
works.
than 0, output 2. We need one more. There's one number missing. X less than 0, x greater than 0. What happens when
Yeah,
x
I meant to
equals?
say x is greater than or equal to 0.
Ah,
The
okay.
lower one.
That's fine. I mean, any way works. You can define the function however you like. Okay, good. So here's 1, here's 2. So I'm going to put an open dot here, because you said if it's equal to 0, it equals 2. So, woo, that's not a very good 2. Good, like that. And I'll put an open dot going to the left, and it's supposed to equal 1 there. Good, perfect. So 0 is in the domain of the function, because if I plug in 0, I get 2. That's good. The limit is undefined because as I get closer and closer to 0, the value of the function near 0 is not some constant. It does not approach some fixed number. It depends on whether you're on the left side or the right side. Good. Okay, let's move up and do one more. This should be, well, actually I have to write a proof, but this one shouldn't be too painful. So 2.1.2 in AOPS. So show using the delta epsilon definition, that for any number a, lowercase a in the reals, we have the limit as x approaches a of just the function x equals a. So we want to prove that, you can just think of this as the line f of x equals x if you like. So we're just showing that for the line f of x equals x, at any input value a, the limit as x approaches a of x equals a. Okay, so how would I start that proof? Basically all delta epsilon proofs start the same way. If you prefer, it might help you to remember the mnemonic I gave about delta epsilon proofs being like a game, or like writing a function, right? Someone hands you an epsilon, you have to cook up the delta, right? So how do I begin a proof that I can cook up a delta when someone hands me an epsilon appropriately? Well, maybe we can look
I
at.
do not remember.
Let's look at. This was one of the proofs that we did last time. This is a little harder. This was proving for a quadratic. So we were proving before the limit as x goes to 3 of x squared is 9, and we started by saying let epsilon greater than 0 be given. Right. So I mean you don't have to say exactly these words, but some variant of defining epsilon as some known quantity will be the first step in every epsilon delta proof, because you always have to say, all right, I'm taking epsilon as an input, I'll tell you how to get delta. So let's write that. Let epsilon greater than 0 be given. Good. So now the next step is I need to, in this proof, tell you how to get a delta, right? So here's the proof we did last time. Here it was a fairly complicated delta. You remember we had to do this argument about choosing the minimum of 1, and then we bounded one of the factors by 7, remember? And then you said, okay, well, let's make it delta smaller than epsilon over 7. So we had to do this fairly complicated rigmarole to get the right delta as a function of epsilon. In this case, it's kind of easier, and you can probably just visualize the line. So in the line y equals x, just the kind of straight diagonal line, if I want my output to be within a distance epsilon of some given input, how close do I have to be to the corresponding input value a? To be between a plus epsilon and a minus epsilon, how close do I have to be?
You would also have to be within epsilon.
Right, yeah, so my input tolerance is also epsilon. So then we can say choose delta to be the same as epsilon. So the line is very easy. You always have to cook up a delta. Here it's the easiest delta you could cook up. Just take the same epsilon and that's all you need. So then all we have to do is explain why that works. So then, and this is where you need the definition, right? So whenever 0 is less than the absolute value of x minus a is less than delta, it is true that the absolute value of f of x, here f of x is simply the same as x, because the function whose limit we're taking is x, so f of x is the same as x. F of x minus a is less than epsilon, which is the same as delta. So we should ask, why is this true? Well, this is simply true because f of x equals x, because f of x equals x. So, I mean, I probably didn't even need to put this sentence or that clause justifying why it's true, because in going from this step to this step, the only difference is recognizing that the function here is the same as x. So if absolute value of x minus a is less than delta, then it's certainly true that absolute value of x minus a is less than delta, because I've just said the same thing twice. Good. So this is our, again, an honest-to-God calculus problem showing that a limit exists, a broad class of limits. So, I mean, this is something we'll absolutely have to be able to do. So questions on this?
I have no questions.
Okie dokie. Alright, let's do one more art of problem solving exercise, and this one, yeah, we might need two slides for this. Okay. So this is 2.1.3. Okay, so the statement is we want to prove that if the limit as x approaches a of f of x equals L, so this is an assumption, right? We're being asked to prove that if this is true, we're allowed to assume this is true. So the limit is x approaches a of f of x equals L, and we have some other number, which I'll call lowercase c, which belongs to the reals. Then this other limit exists. So the limit as x approaches a of this other function, which is c times f. So we take the old function f, multiply it by some number c. The limit as x approaches a of c times f, well, I should write that c times f of x. I think, Logan, you complained about this notation once on your review for algebra, because they wrote a multiplication of functions and then I think it was like an n or something, and it looked very confusing. So this just means take the function f of x, multiply it by c. Actually, I don't know, maybe I'll just write it that way so that we're all very happy. So instead of writing it with that notation, I'll just put brackets around it. The limit as x approaches a of c times f of x. No confusion. Just the number c times f of x. So what do we think this should be? Well, intuitively, if f of x gets close to L and I multiply that function by c, I think the results should get closer and closer to c times L. But of course I need to prove it. Okay, so proof. Alright, we're proving that a limit exists. What should the first step be?
I pressed Alt and forgot that I don't have push to talk on. So
Oh.
since last time we were dealing with proving that a limit exists, we said trying to remember the proper word. Let epsilon greater than 0 be given.
Good.
Whoa.
Okay, let
Oh,
epsilon...
it's blood red.
Oh yeah, I mean, it's the correct color for a proof of limit existence, because that's the nice thing. If we do all these proofs now, then we'll be able to use them later when we're computing things like derivatives and integrals. We won't have to go back and prove these properties, because we can just cite as we've proven before, so we don't have to repeat ourselves. So it's good to get these done. But yes, yeah, let epsilon greater than 0 be given. Now, the next step in the proof is picking the delta. So this is usually where I like to split and do some exploration, because as we discussed last time, usually the exploration part where you figure out which delta you want to use is the hardest part. So, I mean, which delta should we pick? I'll back up to a different slide so we can do some exploring. Okay, so this is like if I were doing a real proof, I would have like scratch paper in front of me and try to cook up the delta and then go back to the main proof. So exploration for that. All right, well, I'll just narrate to you my thought process as we solve this. So we know that the limit without multiplying by c, we know the limit as x approaches a of f of x equals L. That's given, right? So this means for any epsilon, this was not the same epsilon. This is, you have to think of this as a dummy variable. This is not the epsilon that was given in the proof. So the exploration is separate from the proof. This can be a different epsilon. It's like inside a different function in Python. For any epsilon greater than 0, there's some delta. There's some delta so that whenever 0 is less than the absolute value of x minus a is less than delta, it's necessarily true, which I'll write with an implies sign, it's necessarily true that f of x minus L is less than epsilon. So that's given. We know that limit exists. So we can use this. We can use this stuff because it's known. What do we want to show? Now we're interested in, now we want to ensure something different. So the function we're interested in now is c times f of x, right? So we're multiplying by a constant c. And we want that to be close to c times L is less than, well, I don't want to use the same letter epsilon, so this is different from some, I don't know, epsilon tilde with a tilde over it. So this is some other small quantity. So can you see a strategy if you want to ensure that this quantity is smaller than some number? How can you reduce that question to the question we know which is already solved, which is making this quantity smaller than some input number?
Could you simply divide the entire absolute value statement by c?
Yes. Good. So I was going to erase that and move the c over to the other side, but maybe I'll just say it. So this is the same as saying, I'll just rewrite it. So if we divide both sides by c, which we can do as long as c, we should be careful, c is not equal to 0. But if c is equal to 0, then then this function is 0 everywhere. So it's a horizontal line at 0. And we haven't proved it yet, but a constant function has all limits existing. So I'm going to assume for this step that c is not equal to 0, so we can divide by it. C not equal to 0. Good. Then f of x minus L is less than this other thing, epsilon tilde over c. Good. So this reduces it to a previously solved problem. Just to maybe phrase this somewhat more operationally, if this were in the programming analogy, this is like someone hands you a function. It's a black box, so you don't know how it works, but you know this function exists and you can call it. It's like a standard Python library function. And what that function does is it takes in an input epsilon and it outputs some delta, which guarantees that when this number is less than the thing you fed in, the epsilon, when this number is less than epsilon, wrong way. It feeds you the delta so that when this number, absolute value of x minus a, is less than delta, you're guaranteed that this number, absolute value of f of x minus L, is less than epsilon. So again, it's a function. You input epsilon, it gives you a delta such that this is true. Now your job is
I have a question.
Yeah,
Sorry.
go.
I have a question about what we just did.
Yes.
How we were able to effectively divide by c. Would the result be any different if you took the absolute value statement, including the bars, and divided that by c?
The absolute values. Oh, and put a c over the whole thing. You're saying like this? Is that what the question is? Or?
Sure.
Well, okay.
Yeah, just over c.
Yeah, I should have. Okay, I should be a little
Like-
careful. I should really say this thing is less than the absolute value of c. Good. So I agree.
Oh, so. Okay, I don't know how to word this, so I'll see if I can.
Well, here, let me. Okay, let me erase. Well, so it sounds like your question is it true? So, tell me if this. I'm going to try to rephrase your question. Tell me if I'm rephrasing it faithfully. Is it true that absolute value of AB is less than C implies that the absolute value of B is less than C over the absolute value of A? So you're asking, can I divide and then kind of commute that with absolute values to cancel the A inside and put the absolute value on the other side? Is this what you're asking, or is it something else?
Something similar but different. So, if the thing that you're dividing by is inside the absolute value, or like effectively outside the absolute value.
Ah, okay. So, just to use, let me make this as close as possible to our example. So you're asking, is it true that this thing all over absolute value of C is the same as the absolute value of f of x minus L? So I can move this inside the absolute value, and it doesn't make a difference if I write it, outside or inside, basically.
I was thinking a similar equation, except the absolute values bars span the entire height, and the C is not in an absolute value itself.
Ah, so C
as you're writing it right now.
Like this. Okay, so you're asking, are these equal?
Yes.
Yes, so this is true. If C is not equal to 0. So question, answer, yes, if C is not equal to 0. Yeah, so you can take a ratio of absolute values and write that as an absolute value of the ratio. Yes.
Okay.
Good, and we could actually prove that. I'm not going to. There's two cases. You just consider the inside is positive or negative, and then you just write out the two. It's true in both cases. So, yes.
Okay. I've never seen it before, so I had to.
Yeah, I'm now realizing that a lot of the things that are confusing are not the calculus itself, but are just the algebraic steps that I've forgotten are confusing, because I guess they become natural or something. But okay, so you agree then, if you believe me about that that we can divide by the absolute value of c on both sides. On the left, it moves inside and cancels the c's, so we're left with f of x minus L. On the right, we have epsilon tilde over c. Do you agree that's true, assuming that you believe what I just told you on the previous?
Yes.
Okay. Good. Okay, so how does this help us? So if we have, again, this function which is handed to us, we can feed in an epsilon and it'll give us a delta that makes this statement true. And now we want to create a new function to which we'll feed in this epsilon tilde, and it will give us the appropriate delta for this c times f of x and c times L. That's pretty easy. All we have to do is take the ratio, take the epsilon tilde that we're handed, divide it by c, and feed that into the function that we're given. Right, so if we take this quantity and apply this result, that for every epsilon there is a delta for f of x, then to get the appropriate delta for c times f of x, you just take whatever epsilon you're handed and divide it by the absolute value of c. Okay.
So this seems like this would just be, for example, if your function is y equals x, then it's effectively identical to taking the y of 3x, the function y equals 3x, solving for the delta of that.
Yes, exactly. And in fact, let me just go back, because we did that with 3x last week, right? So what did we just prove this week a moment ago? We proved that for f of x equals x, you can pick epsilon equals delta, and it works, right? So what did we do last week when we had 3x? Remember, in that case, we wrote a proof which said, if you hand me an epsilon, I pick delta equals epsilon over 3. Right, here it is. So here's from last week. Right, so the line is 3x. We consider any a. To prove the limit exists, you say, all right, you hand me an epsilon, I pick delta's epsilon over 3, and then it works. So yes, as you've just said, this is identical to the proof that we just did, because we proved for the line y equals x. If it's y equals x, you choose epsilon equals delta. And as you just said, yeah, for any other y equals some other number times x, you would just divide by that. So here you take the choice we had before, epsilon equals delta, divide by 3. Now delta is epsilon over 3. Is that what you're asking?
Yeah.
Good.
I was curious how multiplying by the function was, well, not multiplying by the function, but how it tied into more concrete stuff, quotation marks.
Yeah, that makes sense.
Yeah, I'm wording it terribly.
Yeah, I see what you're saying. It's useful to see a case where, we've actually worked it out and you can see explicitly. And I mean, yeah, this is really all this statement is the thing that we saw last week, which is that if you have a slope, your error gets multiplied, right? So if I want to be between 3a plus epsilon and 3a minus epsilon, but I have a very steep slope, I better make sure that I'm within a third of that error in my input, because my error gets multiplied by 3. All that we're proving now is that same statement holds for any other larger or smaller slope. Your error gets multiplied, so you should really just divide by that to make sure that you're safe. Right. Okay, so let's go back. That was all a big exploration, and now you see why, I've been trying to emphasize this exploring and understanding the statement before you write the proof, because once you get to the proof, it's very short, and reading a proof doesn't tell you anything about how the proof writer actually came up with that idea, right? It's really just like seeing their final polished code, and you don't know how long it took them to debug it or what their first run looks like. But anyway, so how do I write the proof? Let epsilon greater than 0 be given. Choose delta. Well, let me back up, because well, I should add a sentence of explanation for what it is that we're actually doing. So I'm just going to, this isn't strictly necessary, but I'm just going to add the sentence to explain how we're using kind of like the function that I mentioned, which is really the statement that this limit exists. So since we know the limit as x approaches a of f of x equals L, we can find a delta such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L, and here's the key step, is less than epsilon over the absolute value of c. Right, so this is just that step that I mentioned. We're given this function, which is mathematically the statement, we're given that this limit exists. That means we can find a delta for this other epsilon, epsilon divided by root c. Or sorry, root c, absolute value of c. So choose that delta. Then, by simple algebra, which is really just multiplying both sides by the absolute value of c, by algebra, if 0 is less than the absolute value of x minus a is less than that delta that we've chosen, it's true that c f of x minus cl is less than epsilon. So make sure you understand that step, because that was the thing that I explained on the other slide. We multiplied both sides by the absolute value of c, and then use that rule that if I have this multiplied, I can move the c inside. Right? And that's it. That's box, actually, because that's the definition. Okay. So again, reading these proofs, looking at this, it's very hard for the brain to parse, because an epsilon delta proof is very dense, right? Let epsilon greater than 0 be given. Since we know this limit exists, we can find a delta, such that if this is true, choose that delta, and then this holds. It's hard for the brain to parse that, so it's good that you go through the exploration first and see what this is intuitively doing, but then when you convert it to rigorous mathematics, it has to be kind of phrased in this very terse, dense way. This is the way the definition is phrased. But this is a valid proof, so that's box. Questions on this?
I have no questions.
Good, okay. Let's do some of these fun functions then. Well, okay, we saw this last time, right? The x sine 1 over x, so that one's not interesting anymore since you've seen it. Let's do this one. This is sometimes called the Dirichlet function, and I'll tell you a story about this function. I had, in one of my sophomore math classes at MIT, the class was called Analysis on Manifolds. Yeah, that's right. And I had an exam on that course which was very short. It was just 3 questions, and all of the questions were of the form prove or disprove. So they all had a statement, and if it was true, you prove it, and if it was false, you give a counterexample. All 3 of the statements were false, and the counterexample you pick for every single one of the statements was this function, this Dirichlet function. So how do I draw this? It's very hard to draw. So what does this function do? If the input is rational, it outputs 1. The function, if the input is irrational, it outputs 0. So it's hard to draw this because, I mean, there's infinitely many, rationals and irrationals. So it's normally drawn with dotted lines of different sizes. So there are fewer rationals than irrationals. So I will put a kind of sparse dotted line up here at 1. So all the inputs that are rational, I output 1. And then you normally put like a somewhat denser dotted line down here because there's more irrationals. But it oscillates back and forth, infinitely fast. So just to get intuition, what is f of root 3?
That would be 0.
Right, because root 3 is irrational, so that's 0. What's f of 117/50ths?
That would be 1.
Good. I'm going to be tricky. What's f of pi raised to the power e?
I'm gonna say irrational, but that just Is it a trick question because you think it's a trick question?
I mean, you're right, it is 0, but we haven't proven it. I wanted to see if you would comment, because a while back we proved that you can take an irrational number and raise it to an irrational power, and sometimes the answer is rational. So I thought you were going to say, I don't know, maybe it's rational, but yeah, you're right, I'm just trolling. This one is indeed irrational, so it's 0.
Because you have two crazy crazy quote-unquote numbers.
By crazy,
Sure.
I mean the best numbers.
Yes, totally.
Okay, so now let me ask you, does this function have any existent limit? Is there any point, any real number, such that the limit as x approaches that number of f of x exists?
I don't believe so.
Okay, good. That is correct. So at every point, the function's limit at that point a does not exist. Can you explain in words, either by thinking about like epsilon bars or intuitively, or however you prefer to explain it, why is it the case that at any a the limit does not exist?
I do not believe that there is a limit because let's think about how to word. Yeah, I should already be thinking about how to word this.
Maybe I can give you a hint by giving you part of the argument. So remember that, so suppose you want to prove the limit exists, so your job is to pick a delta given an epsilon. So you want to show the limit exists. I come along and hand you epsilon as a half, right? So I give you epsilon as a half, and I say, find me a delta so that as long as I'm within delta of a, all of the outputs are going to be between 1/2 and 3/2. Tell me why you're fucked, why you cannot find such a delta.
As I'm like effectively visualizing how we can find the limits, I want to simply say that because I'm gonna say lower track of irrationals is not taken into account. Yeah, it's not. Why are people pinging me?
Ping ping.
I don't know.
So you're saying, by lower track of rationals, you're pointing out that no matter what delta I pick, here's delta, no matter what delta I pick, if I'm within that distance delta of a, that means I'm in this open interval, every open interval contains both rational and irrational numbers, right? This is related to your almost correct claim. You keep saying that the completeness property is that there's infinitely many of the numbers in any interval. It's not quite right, but the rationals and irrationals both have that property. So I think the claim you're trying to make is that within any interval, there's infinitely many rationals and infinitely many irrationals, so the function has infinitely many outputs that are 1 and infinitely many outputs that are 0. So I can never guarantee that all of the outputs will be between 1/2 and 3/2, because I'm still going to get some zeros, right? Going to get infinitely many zeros. I think, is that close to what you're trying to say?
Not at all, but it makes more sense.
Well, what did you mean by the lower track of irrationals?
Like the way I'm visualizing if something is in a limit is like the more you zoom in, if part of the function is like out of visible range, quote unquote, then it does not have a if it.
Ah, okay. Yeah, that's a
If it-
good picture. So you're saying if I zoom in this much, then I no longer see the irrationals down here. That's what you're saying.
Yes.
Okay. Yeah, okay. I think that's feasible. Good. Other thoughts on...
But there's no way to prove it with that.
Well, no, but I think it's useful for exploration, right? I mean, I keep shitting on intuition and kind of pictures and words. They're fine in the exploration phase. Especially if you're handed a problem that is prove or disprove, like this one. If you don't know whether the answer is yes or no, it's nice to have those kind of non-rigorous pictorial arguments to get an idea of which way you want to try to prove it. But once you decide which way it is, then you have to fall back on epsilons and deltas, because there's just no other way. Good. Other thoughts on this guy?
I have no thoughts.
My brain produces no thoughts. Okay, is this the same? Oh no. Oh, this one's fun. Oh my, I love this one. Oh, sorry. I don't know why I love these functions that oscillate on the rationals so much. I'm going to change one thing. This is almost the same as the previous function. Again, if the input is irrational, so like root 2 or something, it still outputs 0. So I'm going to draw that in as this dense dotted line at 0. The only difference is if the input's rational. Remember, before the rationals went to 1. Now the rationals go to x, which is this line, right? So there's this line. So every rational gets sent to itself. So for instance, f of 2 equals 2, but f of square root of 2 is irrational, is 0. So only one thing has changed. This is f. This pink is f. So now, let me ask you, is it still true that no limit exists? That for every a, the limit as x approaches a does not exist?
I do not believe that a limit exists.
So you think it's still true that for every a, the limit as x approaches a of f of x does not exist for every single real?
Yes.
What about 0?
I'd say 0 is the exception.
So does the limit as x approaches 0 exist or not? Remember, the limit, there's a separate question for every point, right? You don't ask just the one question, does the limit exist, and it applies to every point. You have a separate question for every point. The limit could exist in one place, but not the other place, right? So is it true that the limit as x approaches 0 does exist?
I still do not believe so.
Okay, then give me any epsilon you want. Give me an epsilon, I'm ready. I'll give you a delta.
I guess I can just give you 0.1 and you get to say 0.1?
Yep, you hand me any epsilon and I will pick delta to be that same epsilon. Why does that work? Because if I'm within delta of 0, there's only two kinds of outputs. The output is either 0 or the output is the same as the input, f of x equals x. So if I'm within delta of 0, I can guarantee all of the outputs are also within delta of 0, right? We proved it for the line, and for the constant f of x equals 0, I don't need to worry about it because their distance from 0 is 0. So they're fine. So this actually has the same proof as for the line y equals x. Another way to think about it using your zooming argument is if I zoom closer and closer and closer to the point 0, eventually as I zoom in I get just the line which is close to 0, or the line y equals x, and the horizontal line y equals 0. But all of those points are staying within my magnifying glass. There's no points up here, there's no points down here. If I'm within delta here, or sorry, my delta should be the horizontal one. If I'm within delta here, I can guarantee all the points are within delta here. I sense tension that you don't want the limit to exist, so ask me questions. Or give me a counter argument.
I mean, it makes sense.
Okay. Do you see why the limit does not exist at any other point?
Yes.
Good. So if I'm here, I'll again use your zooming argument. If I'm here, all I have to do is pick a zoom which starts to exclude one of the points on the bottom, right? So if I'm around this point, I just set my epsilon bars to be like this, and now I can no longer see the points down here. The only exception is this point 0, because in some sense the things I have to keep in my crosshairs get closer and closer and eventually touch at 0, so I just have to keep my eye on this. Okay. So I won't write out the proof for this one because it's the same as for the line y equals x. Now this is beautiful. This is one of the best functions in all of mathematics. This is, as I said, sometimes called the stars over Babylon, or more correctly, Thomae's function.
Thomae?
T-H-O-M-A-E. So the Thomae function.
Who names their child that?
Hell if I know. Alright, so I should explain what this function does. The bottom part is the same as before. If it's irrational, the function outputs 0. The rule is more complicated if the input is rational. If I hand you any rational number, we know that number can be written as p over q, where p and q are integers. So here's the rule. I hand you a rational, you write it as p over q, you simplify, put it in lowest terms, so if it's like 4 over 2, you have to simplify that to 2 over 1. When you're all done simplifying, take whatever the denominator is, and then output 1 over that denominator. So I'll give you an example. If I hand you the input 1/2, that's already in lowest terms, so I just take the denominator, which is 2, and then I output 1 over 2. So we can see that on the graph, right? So here on the x is 1/2, and you see the output for 1/2 is also 1/2. So that's fine. But if I input 3/2, that has actually the same output, because 3/2 is in lowest terms. So q is 2. So again, I output 1 over q, which is 1/2. And again, as you can see, I don't know if you can read it, but this is 3/2 on x, and 3/2 gets mapped to 1/2. Okay, so let me ask you, if I input 5/9, what does stars over Babylon output? F of 5/9.
I believe it would output 9/5. That is a total guess. Wait.
Let's be careful. So this is p over q in lowest terms, right? So p is 5, q is 9, and the output is 1 over q.
Oh. Okay, so 1/9.
1/9, good. So f of 5/9 is 1/9. Good. Good.
Okay.
So it's always just 1 over the denominator. Good. So this thing never gets bigger than 1 in particular, right? So it's always going to be 1 over some integer, right? Because q is always a positive or negative integer. So this thing's upper bounded by 1, right? And it's going to be 1 on all the integers. So f of 5, for instance. F of 5 is going to be 1, because 5 is written as 5 over 1 in lowest terms. All right.
Can you put piecewise functions into Desmos?
Can I put what kind of function?
Piecewise functions.
I don't know what Desmos is. Is that a graphing thing?
Yes, online.
Maybe. You can put them in Mathematica. Actually, it's quite useful. I do that quite a lot. I don't know about Desmos, though. But, okay. Now for the killer question, and this takes some serious thinking. Does stars over Babylon have any existent limits? Is there any number a, such that the limit as x approaches a of f of x, where f is the Thomae function, exists?
I do not believe so, because the closest item, well, yeah, I don't believe that there is a possible limit, because as they approach, for example, that as this function approaches any integers, it seems that this just jumps back up to 1, jumps quotation marks.
Well, remember when we compute the limit, we don't have to worry about the actual value at that point, right?
Okay.
So if we look at, you said integers, yeah, so let's just look at 1. If I look at the limit as x approaches 1, we don't worry about what actually happens at 1.
Yeah.
Remember, that's that definition, 0 is less than absolute value of x minus a, right? So you got to remember that's not less than equal. But it looks like... Sorry, what did you say?
Okay. Just the point that it looks like it's going to land at.
Yeah.
Okay, so yes, at the integers there is limits.
Okay, so what is the limit as x approaches 1?
As x approaches 1, I believe that the limit is 0.
Good. Okay. So it has a limit at 1. Now I'm going to repeat your argument. Let's look at a half. Let's see what it gets close to at a half. I don't have to worry about what happens at 1/2. But can you see why it's starting to pile up at the bottom near a half as well? It's starting to pile up near 0 here. It's actually the same argument you just made at 1. At 1 it piles up at 0. At a half it piles up at 0 as well. So do you think the limit exists at x equals 1/2 as well?
Yes.
Good. Yes, so the limit as x approaches 1/2 of the stars over Babylon is also 0. Alright, let's go to a third. It's kind of hard to see, but the exact same argument applies there. It's at this point it's just because the size of pixels is too large that we can't actually tell, but this image is a fractal. Can you kind of guess? I'm just going to draw an orange box here. See this box which just touches a half? Can you see that that box, if I zoom in on that, it's going to be kind of a copy of this box where this box just touches 1? Can you kind of see that if you just kind of scale, that's a bad box, but if I just zoom in on the box centered at a half, it's really a copy of this thing contained within itself?
Yes.
Okay. So that's one way to argue non-rigorously.
Oh boy.
Yeah.
Okay.
So amazingly, and this is one of those times that you have a certain, for me, when you have a certain experience realizing a mathematical truth that you never would have guessed, and for a moment your mind just kind of goes blank, and it's like you're seeing the mind of God. And I mean, there's only very few.
The mind of God. Welcome to Germans.
Literally, Einstein said, mathematics is like reading the mind of God. I mean, there's very few experiences in my life that have been quite as profound as realizing deep truths like this. But amazingly, the limit exists at every single point. Every point of this function, the limit as x approaches a of f of x exists, and it equals 0. That's remarkable to me, because this function is somehow the least smooth you could possibly imagine. There's no kind of connected curve anywhere. At every single point, it jumps back and forth between 0 and these fraction values infinitely often. And nonetheless, the limit as you approach any of those points exists and it equals 0. Sorry. The limit exists and it equals 0. So we can actually prove that. I don't know. I might leave it for you as an exercise, or I might write it up as an example, because there's one subtlety in the proof. You have to use the fact that there's kind of finitely many integers. So you've given an epsilon, you say, all right, I'm going to pick some integer n such that 1 over n is smaller than epsilon, and then you say, okay, there's only so many denominators that are smaller than n, so I just move in to make sure none of those denominators are in my window, and then everything is within epsilon of 0. So it's slightly subtle. Maybe I'll write out the proof afterwards. But I think that's remarkable. Thoughts or questions?
Okay. You said Einstein. Was that because that was his quote? Because it said Germans.
It was because his quote about reading the mind of God, but it happened to coincide
Okay.
with Germans.
Also, your mic suddenly got better. I don't know why.
Wonder if it's actually the mic or if it's just the Wi-Fi speed or something.
It could probably be the connection. I think Discord uses a dynamic algorithm.
Ah, okay. Good. All
I
right.
have no questions or comments about this specific.
Are you happy? Are you as happy about it as I am, though? At least.
I'm grinning. Is that good enough?
Good. I mean, this is the sort of shit I live for, is seeing that. I mean, if that does not convince you of this quote, that a function is a very, I mean, the range of functions is a huge zoo of creatures. They're not just smooth things like parabolas. That thing is a beautiful function, and it's a very complicated rule, and it's hard to visualize. So that's, I don't know, a good instance, I think. But okay, well now I will ask you, since we've been doing limits for quite a while. I can either continue telling you about limits and continuity stuff, or I can talk about some of the consolidation document problems.
How far are we in? When did we start again? All started at